to the exercise, this video on an exercise of Fourier series. In this exercise, we will calculate the Fourier series, the coefficients of a square train. A square train, or a train of square impulses, is a wave that has the following analytical expression. Xt, it's the infinite summatory to coefficients k, for example, of pi waves or pi signals, which are kt apart one from the other, and which have a width of tau. If we draw this, what we get is the square wave. If we plot x of t as a function of t, we get the following drawing. We will have a first square here, which corresponds to the value of k equal to 0, and it has a half width of tau divided by 2, or what is the same, a full width of tau. And the next train, or the next impulse, will be t, capital T seconds apart, and the same on the negative part, okay, on the negative part, exactly the same. So goes to the left and goes to the right. For example, this one will correspond to the index k equal to 1, and this one to index k equal to -1. So we want to calculate the a sub k, the Fourier series coefficient corresponding to xt. Okay, so we apply the formula, which is 1 divided by the period of the signal, and the integral to any period that I want to do that, of x of t, the signal that I want to get the Fourier series from, times e to minus j k omega 0 t, and the variable of integration is t. Remember that omega 0 is 2 pi divided by the period of the signal, 2 pi divided by 2. Okay, so we calculate this. This will be 1 divided by the period of the signal, which is capital T, and then the period that I choose is this one, the fundamental one, that one that goes from minus tau divided by 2 to plus tau divided by 2. I could have used any other period, but I used this one. And then xt in this period, the value is 1. So will be 1 times, and then the exponential, which is e to minus j k omega 0, which is 2 pi divided by capital T times t dt. Okay, so this is a very simple integral. It's immediate. I leave it for you. And the result of that is the following. It's j divided by 2 pi divided by capital T, the period, times k, which is the coefficient, the index, and then is sinus of k times tau divided by capital T pi. And now remember the very important signal that you show in the first part of the subject, which is the sinc signal. Remember that the sinc signal of whatever thing is as an argument of the sinc, it was the sinus of p times this thing that is inside of the argument, the sinc of p times that, divided by pi times the same thing. Okay, remember the definition of the sinc. So if we apply this to this expression here, you can get that this is tau divided by capital T sinc of k tau divided by capital T. Okay, so these are the coefficients of the Fourier series of this periodical plane of square impulse. Okay, but let's keep it a bit forward, and let's plot the amplitude spectra, or a spectrum. Okay, remember that the amplitude spectrum is drawing as a function of k the modulus of the coefficients a sub k. And we put the modulus because you can see that those coefficients can be complex or complex. So if we want to completely draw them, we would need to draw the amplitude, the modulus, and the phase. But in this case, let's just focus on the modulus. If you draw the modulus of this, which is basically this thing over here, okay, what you would get is the following. You will get this. You have an envelope, okay, and basically what is a rectified sinc, okay. So I am drawing the modulus of this. Sorry, there is a j here that is missing, okay. So this will be the envelope, and then the values of the coefficient would be for k equal to 0, I will have the value here. For k equal to 1, I would have another value, let's say over here. For k equal to 2, I may have another value here, and so on. Okay, so the real values, the values of the coefficients a sub k, are points on the envelope. And again, for example, this is the point corresponding to k equal to 1, so this will be in the value tau divided by t. This second one will be in the value 2 times tau divided by capital T, and this will be, for example, in 3 times tau divided by capital T. And the same exactly to the left. I don't write it. Okay. So this will be the shape. But the question now is, okay, will ever any of the coefficients be 0? So will some of these coefficients sometimes it's possible that they are right where this rectified sinc goes to 0? So let's see for this, okay? So what we are wonder, in other words, is where are the zeros of the sinc function, okay? Remember that this is a sinc function, a rectified sinc, actually. This is a rectified sinc. So the zeros of a sinc of whatever, remember that the way to calculate the zeros of a sinc of a certain argument, what you do is you equal this argument of the sinc function to the integers plus or minus 1, plus or minus 2, etc. So by equating this over to these values, plus minus 1, plus or minus 2, we will get the position of the k in the k variable where the zeros are, okay? So in our case, the argument of the sinc is k times tau divided by capital T. This is the argument. So to find the values where the k's, where the sinc has a 0 in a certain k, so we equate that to plus or minus 1, plus or minus 2, etc. Okay, so if we take apart k from here, what we get is the values of k where the sinc would be 0, which again will be plus or minus capital T divided by tau, plus or minus 2 times capital T divided by tau, etc. Okay, so if it happens that some of those values are integers, okay, if some of those values of plus or minus t divided by tau, plus or minus 2t divided by tau is integer, then the corresponding coefficient a sub k will have modulus equal to 0. Okay, that's the condition. Okay, so in general, the division of capital T divided by tau will not be an integer times 2, times 1, etc. So in general, the situation will be this. But for certain values of tau and t, it may happen again that some of the values of the a sub k will be 0, because instead of being here, for example, they are here. Okay? But let's move a little bit further in this exercise, and let's see what happens. Let's do a special case, which is the following: special case or a special situation, which is when the tau value equals the capital T. Let's see what happens. Okay, so if the capital T is the same as the T value, what happens is that these coefficients plus or minus capital T divided by 2 plus or minus 2 times capital T divided by 2, etc. All these values are values which are what? Are always integer, okay? Because tau is equal to tau, capital T, so this will be plus or minus 1, plus or minus 2, etc. So in this case, all the a sub k are 0, okay? If you just apply what we found over here, okay? So what is really going on here? How is this possible? Then all the coefficients are 0, and it makes sense. Why? Because first, look at the envelope of the coefficients, a sub k. Remember that the envelope was a rectified sinc, which is this one, and the same on the left, okay? The same on the left. What is happening is that in this case, all the coefficients but the first one are 0, because the coefficients are right where the rectified sinc value zeros, okay? So, for example, this will be the coefficient a sub 1, this will be coefficient a sub 2, and so on and so forth. So it is clear, the only one that is not 0 is this one, which is the DC component, the average of the value of the signal, okay? And does it make sense? Of course it makes sense, because if you look at the signal, in this case, of tau equal to t, so if you plot x of t, how would you plot it? Well, you will have the fundamental period here, okay? But as tau equals to t, the next one will be right on the right here, okay? And the same on the left, the other square will be just touching, okay? So you will see that, for example, this is the value tau divided by 2, which in this case is exactly as capital T divided by 2. So what are we having? We're having a signal which is a constant signal of the value, well, in this case, 1, okay? The average value is 1, okay? And it makes sense that a signal which is purely a DC component has just a unique single component, which is a sub 0, which is the average value of the signal, which is 1. Okay, so it makes sense. And finally, let's do another special case. You can see that this is a very rich exercise. The other case is another special case. Imagine that in this case, the tau is much less than the capital T. Remember that the tau has to do with the width of the fundamental period, whereas tau is the separation between those signals. Okay, so in this case, the separation is much bigger than the width of the signal. So in this case, the signal, how would it look like? It will look like this. You will have, for example, a fundamental period which is very slim, very slim, you can see here, because tau is very little, and then the next one will be very far away. It will be like here, and the other one here, okay? So this is the case of tau, which is this width, is much smaller than capital T with it, which is 1, which is this one, okay? In other words, the division of t divided by tau is very big, or the case which is a tau divided by capital T is very, very small, okay? So if you do that, you will see that the coefficients in this case, how would they look like? They will look like this. As always, we draw as a function of k the the modulus of the coefficients a sub k, and of course we always have here the envelope, okay? The rectified envelope, which is the rectified sinc, okay? And in this case, the coefficients will be very, very close. You will have one here, another one here, another one here, okay? And these points are the coefficients that now are very, very close one to each other. So this one could be, for example, the coefficient which is in k equal to tau divided by 2. This could be the coefficient of 2 times tau divided by, by tau. And this is, this is t divided by tau divided by t. Well, so in this case, if the impulses are almost like delta functions, then the result is that the spectrum of the amplitudes is almost a continuous signal. Okay, so this will be what will drive us to define the Fourier transform, which is something that we will do in the next topic of the subject. Okay, I hope it has been clear. Enjoy it, and we will see each other in the next video. Bye-bye.